Okay, so the first one up here, where do we start? From the center, we go down 3. And from there, we go up 1 over 2. Very good. I'm going to do it one more time just because those points are kind of close together. There's my line. Number 2, where do we start? Up 2, yes. This is the number that's not multiplying the x, so it's where we start. It's positive 2. Now this is negative 3x. How do we treat that? Negative 3 over 1. So from here we go down 3 over 1. The over is always positive. It's only the rise that is positive or negative. Number 3 here, we got to do some adjusting. What would we have to do? We have to get y by itself. So if you get rid of the 2 and the 1, the 2 is multiplying it, and the 1 is added to it. So we have to go backwards. We have to subtract the 1 first. So let me rewrite this up here. So we're going to subtract the 1. When we subtract or add, we only have to do it to one piece on each side. So we subtract 1, takes that away, leaves me with 2y. Over here, I'm going to subtract 1 from the negative 1. That becomes a negative 2. The 3x is unchanged. But now we do have to divide by the 2 to get y alone. When we multiply or divide an equation, we have to do it to each digit. So here, this digit's divided. The 2 divides out, leaving me with y. Over here, 3x divided by 2 is 3 over 2x. We just turn it into the numbers into a fraction. Negative 2 divided by 2 is negative 1. So where are we going to start on that one? Oh, that should have been 3. You are correct. So that would have been 3. That'd make this 4. That makes this 2, doesn't it? Sorry about that. So yes, I copied it wrong. That should be minus 3. So when we subtract 1 for it, this should be a negative 4 here. So when you divide by 2, negative 4 divided by 2 is a negative 2. Good catch. So that means we're going to start where? Down 2, right here, negative 2. And from there, we're going to go up 3 over 2. And there it is. The last one is going to require a little bit more work. We have to get rid of the 2x. It's added. Negative 3 is multiplying y. 2x is added. So we're going to subtract the 2x first. So we're left with negative 3y equals 6 minus 2x is just 6 minus 2x. Then we're going to divide by negative 3. Cancels out negative 3, so y equals, what's 6 divided by negative 3? Negative 2. And negative 2x divided by negative 3? Positive 2 over 3x. So where do we start? Down to it, negative 2. And from there we go up 2 over 3. There it is. Any big questions on those? Okay. So that's the big part of graphing you need to remember how to do for the test coming up 1 week from today. Just so you guys know, hopefully we'll take some time. We'll have some time to review this Thursday because there's a lot of stuff on this test coming up. Geometry and this basic graphing and statistics. So there's open note, open books, of course. But of course, next Tuesday is our last class. So there's not going to be a lot of time to get your tests back into corrections. I am going to make every effort to have them graded by about 10:30 Wednesday morning. So if you want to stop in here, those of you at New Richmond, Hayward, or Ladysmith, I will email them back to you as soon as they're graded. So make sure you check your email, WITC email, sometime before noon on Wednesday to get your test. Hopefully sooner than that. Those of you here at Rice Lake, if you want to stop in sometime around noon or 11:30 on Wednesday after the test, try to pick it up. You can do corrections and get it back to me. I am here until 4:30 Wednesday. So if you get it to me by then, I can put it in. If you need a little more time, I will be back in Thursday morning to finish up my grading and submit. So if you throw it under the door here by the time I get here Thursday morning, which will be about 8 o'clock, just so you know. So basically hang around Wednesday night and get it done if you need to. If I have to, I can hang around. My last class ends at 4:30 Wednesday. If there are people here that want help with corrections, I will stick around Wednesday night and help you with them. Okay. So yeah, usually we have an extra class, but for some reason this semester we got short. Well, there's only 15 Thursdays this semester, I think is what did it to us. So at the end of class last time, we were talking about organizing data into these tables, these frequency tables. So let's take a peek at how that all works out for us. We remember we had two types of data, categorical and numerical. For a frequency table, we might have had like favorite color. Maybe I gave you the choice between blue, red, and green. For numerical, we may have had height. This is a frequency. Your height, of course, I can't list every individual height, so I might do ranges. We might have done 60 to 63.9. Let's do 60 to 62.9. 63 to 65.9. 66 to 68.9. 69 to 71.9. And 72 to 74.9. So we had ranges there. We couldn't list each individual height. For frequencies, let's say over here for color, we had frequencies of, let's say blue was picked 18 times, red was picked 21 times, and green was picked, I'll always do 11 times, make it work out easy. For height over here, let's say we had 3, 8, 15, 11, and 4 in those groups. Again, those are numbers I just pulled out of the air and put in there. We normally would have a list of numbers and we'd have to organize them. The reason I put these frequency tables up, there's one, to remind you what they look like, but two, we're going to look at expressing these with graphs today. We talked about this just a touch last time. Now I want to put the difference side by side here. We'll put a bar graph next to what is called a histogram. The histogram, a lot of people look at it and think, well, it's just a bar graph, but there is one key difference. The bar graph is expressing categorical data. So I'm going to have red, blue, and green down here. And let's see, I've got a number at least up to 20. So we're numbered up to at least 25. Red was 21, right? Yeah, red 21. I don't know why I changed the order. Blue was 18. Green is 11. Now, one of the weaknesses of a graph is if I wanted to know exactly what number green was, it'd be really hard to see here. Oops, helps if I draw that line straight. It'd be really tough to see here because I follow it over. Well, is that at 10 or is it 11 or where's it at? Getting exact numbers off a graph is not what they're for. But what it is, I can very quickly look at this and say green was the smallest and red was the most. Now over here, instead of having colors down here, this is going to be the 60 to 62.9, 63 to 65.9, 66 to 68.9, 69 to 71.9, and 72 to 74.9. And let's see, we got to go up to 15 for that one. So let's see, 3, 8, 15. So we've got 3, 8, 15, 11, and 4. Now, one thing that sticks out as obviously being different here is the fact that there's number ranges down here instead of categories. The histogram has number ranges instead of categories. It's numerical data. But the other difference that you probably saw was that these bars touch each other. They're tight together. There's space between these. There's actually a valid reason for that. There is no connection between red, blue, and green. I can put them in any order I want to. There's no logical order or connection between them. There is a connection between these. These categories have to go in that order because that's the order that they numerically go in. And they do connect to one another. 62.9 is followed by 63 and so on. So connecting the bars is the way of visually showing that connection between the groups. It's kind of, there's a lot of psychology that gets involved in the study of statistics. Other graphs we could do, we talked about circle graphs a little bit. To do a circle graph, normally a circle graph is done for qualitative or categorical data. Let's take my colors up here again. What we would have to do to create a circle graph is usually we find percents. So instead of just having the frequency here, we would find something called the relative frequency. To do that, we first have to find the total. We add these all up, and that should add up to 50. So up here for the relative frequency, this is 18 divided by 50. That's 0.36 or 36%. 21 divided by 50 is 0.42 or 42%. 11 divided by 50 is 0.22 or 22%. Now, years ago, what we would have done is we would have said, okay, 36% of 360 degrees is, and then we would have taken our protractor and measured out that exact angle. Well, now we have so many computer programs that would give you a perfect graph. We don't have to be perfect. We just have to be close enough. So we're just going to use some benchmarks. Half of a circle is what percent? 50%. Quarter of a circle then would be 25%. If I cut a quarter in half, an eighth of a circle would be half of 25 is 12.5%. We can use that to get a pretty close approximation of most of these. For example, 36% here. 25 plus 12.5 would be 37.5. 36% is just less than that. It's probably something like this. That would be the blue. 42% is a little less than 50. 22% is a little less than 25. So I think of the green here as being just less than a quarter circle. Something like that. There's my green. Everything's a touch big. There, like that. So less than 25%. Of course, the rest has to be the red. 42% is a little bit under 50%. For our purposes, that's close enough. But the big deal, the big thing is to find the total and then divide each of the frequencies by the total to get the percent for it. Another graph we might use is called a line graph. And a line graph expresses change over time. For example, let's look at, if we divide the semester up into, let's divide it up into 4-week chunks so we don't have so many to do here. So let's look at your grade at the end of the first quarter, second quarter, third quarter, fourth quarter of the semester. Let's assume you never dip below 60%. Obviously, you're not going to go above 100%. So let's say at the end of the first quarter, you're at 83%. The end of the second quarter, you struggled a bit with fractions. You dropped down 71%. Third quarter, you came back up to about a 74. Fourth quarter, you climb back up to about 83% again. Now, a line graph is not comparing many different things to each other at a single point in time. These other graphs, the bar graph, the pie graph, those are snapshots. Those are single point in time, different, one variable, different categories being compared to each other. This is one thing, one category being compared over time. It changes over time, sometimes referred to as a time series. What a line graph is good for, what its strength is showing those changes. By the way, a lot of people are tempted to do that. Don't do that. It was not 0 at the beginning of the quarter, so that line is nonsense. So make sure you don't do that. But what this does show us, very quickly by looking at the line graph, you can tell that it was increasing here and here because the line is sloping upward. And it was decreasing here because the line is sloping downward. Obviously, that's decreasing fastest between the first and second quarter because that was the only place that's going down. But where did your grade increase at the fastest rate? Well, from the third to fourth, because that's where it's the steepest going up. And that's what the line graph is strong at. Again, if you wanted to ask what was your percentage at the end of the first quarter of the semester, well, we know it's somewhere in that 82, 83, 84, but we can't get an exact number. Because again, graphs are not good at exact numbers. That's where you go back to a table. Okay, so enough of the data graphs. Let's start looking at the numbers. So we are going to take a look at data distributions. Distribution of data is basically its shape. And what we're talking about is we're taking a number line that covers the whole range of data. So let's take a look at maybe grades in this course. So let's say we got final grades that range from 40 to 80 on up to 100%. And so let's say we look at students. I can shade this back a bit, can't I? So let's say we take a look at students. We're going to put all the students over the last, well, we've been teaching this class now for like 9 years, over the last 9 years of the course and look at what their final percentage is. So let's say we got one student here who's got an 82. I'll put a dot above 82. We had a 93, put a dot there. 79. 81, 87, another 82. We just keep putting dots in where their score was, their final scores. And what happens if there's already a dot there, we put one above it. You can see what happens is this starts building up and it starts making a shape. Is it going to get really high way out here? No, because hopefully there's not a lot of really low scores. Going to get really high way up here? Well, same again. No, hopefully not. as we get all these dots in here to represent all these students and their final scores, it starts to take on a shape. That shape is the distribution. And usually, normally, that shape will look something like that. You've probably heard the phrase bell curve. That's what they're talking about. It's actually called the normal curve because that is the shape that data normally takes. Most natural data distributions have a normal shape or a bell shape to them. So when we're looking at this distribution, there's two things we can use to describe it numerically. One is the center of the curve. So if I'm looking at that curve versus this one here, how would you describe the difference between the blue and the black curve? The blue one is shifted to the left, or it's lower. It has this lower center. But if I wanted to compare the black to the red curve, how would I describe that difference? Their center's at the same place, but the red one is narrower. That's what we call spread. Sometimes called dispersion. So numerically, we need to describe the center of these distributions, the center of that curve, and the spread, how wide it is. So let's start out talking about the center. So to talk about center, I'm going to put a list of numbers over here that we're going to use. And it's just going to be a small list. So here's my list. I only have 5 numbers there. First thing I'm going to talk about here is size of the group, sample size. The symbol for sample size is the letter N. So for this sample here, N equals what? 5, because there's 5 numbers in that list, in that group. So to measure center, the first measure of center that we use is called the mean. The mean is what most of us have been taught since about 3rd or 4th grade. It's called the average. To do it, you add the numbers up and divide by how many are there. So the symbol for the mean is x bar, x with a bar over it, is equal to this little symbol means the sum, and I'll just add up all the x's, all the values, and divide by n. Divide by how many are there. So that means we're going to do 27 plus 18 is 45 plus 31 is 76 plus 28 is 94 or 104 plus 24 is 128 over 5. 128 divided by 5 is 25.6. There's our mean. Any questions on the mean? Second one, it's called the median. The median is just the middle number. If we get time to talk about percentiles, it's the 50th percentile. Well, to find the median, we have to go through a couple of steps. Step 1, put the numbers in order from smallest to largest. So let's see, we got 18, 24, 27, 28, and 31. They're in order, smallest to largest. Step 2 to finding the median is to find the position. So this can be done one of two ways. if n is odd, now I'm starting with that because for this data set, n is how much? 5. So n is odd. You're going to take 0.5 or 1/2. Where the median is in the middle, that means half of the data is smaller than it, half is larger than it. So you're going to take 0.5 times n. So for this, that's going to be 0.5 times 5, which will give us 2.5. If you get a number here that is a decimal, that means you will round up. To the third place, the third number in the list. So if I number these as 1, 2, 3, 4, fifth number in the list. The third number in the list is 27. So the median here is 27. The other case, what if n is even? I'm going to have to use a different set of numbers here, so I'm going to make a new set of numbers. I'm going to put them in order from smallest to largest as I make it so I can avoid, so I don't have to do that step. So we're going to go 12, 19, 22, 23, 32, and 37. So here n is how much? 6, because there's 6 numbers, right? So the position is going to be 0.5 times 6, which is 3. Since that is a whole number, in other words, no decimal or fraction, the median is between that one and the next one. So it's between the third and the fourth number in the list. So I come up here, 1, 2, 3, 4, 5, 6. The median is between the third and fourth number. How do I find what's between them? I add them together and I divide by 2. When you do that, by the way, make sure you hit equals before you divide by 2. Otherwise, your calculator will divide not before it adds. It ends up should be in 22.5. So it'll be the median of this set of numbers. This next one's only useful really in really large sets of numbers. The mode is the number that occurs the most often. In both of the groups we showed so far, no number appears more than once. So neither of those groups have a mode. Like I said, a mode really is only useful in really large sets of numbers. So I'm going to make a large set of numbers. Now for mode, you do not have to put the numbers in order from smallest to largest, but I'm going to anyway just because it helps me keep track of what I'm writing down. So here in this set of numbers, can you see a mode in there? You got the 18 and you got the 21 that are both repeated twice, right? Now depending on the textbook you're working with, some textbooks will say there's one mode or there isn't one. Others will say you can be bimodal, you can have up to 2 modes. Others will go into some long formula. The bigger the data set, the more modes you can have. You can have, the square root of n minus 1 or whatever. For our purposes in this class, there's either one mode or there is none. So for this group, even though both the 18 and 21 appear twice, we'd say there is no mode because there is no single number that appears the most often. So like I said, the mode is really only useful for extremely large sets of data. So the big question, which is best? Probably already seen my prejudice against the mode. So let's just talk between the mean or the median. So a lot of people, well, who would say the mean is the best measure of center? Couple. Median? Don't care? Okay. So it's about 50-50. In a lot of groups, people say the mean because they've been doing it since they were a kid. It's an average. You're adding numbers together and you're dividing. You're doing math. It feels like you're accomplishing something. But I'm going to throw up a set of data here. Okay, let's find the mean and the median for this set. The mean would be 7 plus 11 plus 12 plus 14 plus 20 divided by 5, because there's 5 numbers in that list. That's 18, 30, 44, 64. Divided by 5 is 12.8. The median, well, to set this small, you can pick out the middle number. It's 12. Otherwise, it would do, 0.5 times 5 is 2.5, rounds up to the third number in the list. I'm going to do another list of numbers over here. Now you can see the first 5 are the same. The next one is going to be a little larger. So for the mean, now I'm going to add them up, and it's going to be 144 divided by 5, which is 28.8 for my mean. My median now is going to be between the third and fourth number in the list. So that'd be 12 plus 14 divided by 2 is 13. Which one was more unstable when we put in a really large value? Well, the mean, it jumped from 12 all the way up to 28. For the median, it jumped, but it only went from 12 up to 13. In general, in statistics, the median is considered to be the better measure of center because it's more stable. One really large or one really small number doesn't set it off too bad. Now, in a good set of data, the mean and median should be pretty much the same anyway, so it doesn't matter if you have a good set of data. The only way it matters is if you have a really, like I said, a really skewed set or a really big outlier. Let me show you an example of this. 1983, University of Virginia. Advertised that the average starting salary of a marketing graduate, four-year marketing graduate, was right around $78,000 per year. Well, that's pretty good money. I'd be tempted to leave here for $78,000 a year. Think about in 1983, the average high school teacher was starting out with $16,000 or $17,000. What they neglected to tell you was that one of the graduates in that class with a marketing degree was a man by the name of Ralph Sampson. Mr. Sampson was 7'4", played on the University of Virginia basketball team, was the two-time NCAA basketball player of the year, and was drafted #1 overall by the Houston Rockets. He made several $1 million that year. It takes a lot of $20,000 marketing graduates to average a multi-million-dollar contract down to $78,000. In fact, he was the only one in the group that made more than $33,000 that year. So only one person made more than the mean. The median has to be right in the middle. Half of the group's going to be smaller, half of the group's going to be larger. So this had to be the mean. All they said was average. They didn't say mean or median, but it had to be the mean. The median of that group was actually right around $24,000. So still actually pretty good money compared to what salaries were at that time, but not nearly as outstanding as $78,000. Let's talk about measures of spread then. Our easiest measure of spread is something called the range. The range is the maximum minus the minimum. The maximum is the largest number in the list. The minimum is the smallest number in the list. So let me give you a list of numbers here. What's the range of that list? Largest number is 28, smallest number is 12. It's a range of 16. Let me give you another list over here. What's the range of that list? Well, 28 minus 12, it's going to be 16, isn't it? Would you say that those two lists are equally spread out? No, I would say this one here is a lot less spread out. The numbers are concentrated in the middle, then we just have the two out on the ends. These are pretty evenly spaced. They're spread out. So the range is not an adequate description of spread. So we use something called standard deviation. And along with standard deviation, we're going to talk about variance a little bit. Now, there is a really ugly formula for calculating standard deviation and variance. I'm not going to show it to you because it's kind of ugly. Variance is a 5-step process. Standard deviation just adds an extra step to that to get the standard deviation. So let's go through it. The first step is to find the mean. So X bar here, we're going to look at this set first. 12 plus 16 plus 20 plus 24 plus 28 will be divided by 5. Well, that's going to be 100 if we add that up, so it gives us a mean of 20. Step 2 is to subtract that mean from each number. So we have 12, 16, 20, 24, 28. We are going to subtract the mean, which is 20, from each. 12 minus 20 is negative 8. 16 minus 20 is negative 4. 20 minus 20 is 0. 24 minus 20, positive 4. And 28 minus 20 is 8. Now, by the way, if you wanted to double check at this point, I mean, it's not really part of the calculation, but if you double check, this should add up to 0 at this point. If your mean is correct and you subtract it correctly, those should all add up to 0. Step 3 is to square each difference. The difference is the result of a subtraction. So that's what we got here. Each of these is what we would call a difference. So we are going to square those. Negative 8 squared is, yes you can. You can't square root it, but you can square it. Negative 8 times negative 8 is 64. Be careful on your calculator. Because if you type in negative 8, hit x squared, it might tell you negative 64. When you square a negative, you got to put it in parentheses like I did here. Or it's going to do the squared first and then add the negative to it. Whenever you square something, it will always be positive. That's why you can't square root a negative, because there's nothing you can square to get a negative. So negative 4 squared is 16. 0 squared? 0. 4 squared? 16. And 8 squared is 64. So that's step 3. Those should all be positive. Step 4 is to sum those up, to total those up. If we add all those, we get 160 total. Step 5. Is to divide by n minus 1. So for this data set, n equals how many? 5, right? So n minus 1 equals 5 minus 1, or 4. So we divide by 4. 160 divided by 4 is 40. That number right there is called the variance. If we were going on to inferential statistics, the variance is important for doing some of our tests. For our purposes of just describing the spread, what's more important is a number called the standard deviation. Standard deviation is the square root of the variance. So in other words, the square root of 40. So it's just an extra step. Square root of 40 is 6.32. That's the spread of those numbers. That's how spread out they are. Now my other data set was 12, 19, 20, 21, 28. And we said those look like they're less spread out. Let's find the standard deviation of them quick. What's step 1? Find the mean. What's the mean of that set of numbers? It's 20. Add them all up. They add up to 100. Divided by 5 is 20. What is step 2? Somebody said it over there. Subtract the mean from each. So we got 12, 19, 20, 21, and 28. I'm going to subtract 20 from each. 12 minus 20 is negative 8. 19 minus 20 is negative 1. 20 minus 20 is 0. 21 minus 20 is 1. 28 minus 20 is 8. Again, if you wanted to, you could add those all up and that should equal 0. It's just a double check. It's not part of the calculation. What's the third step? Square them. So negative 8 squared. 364. Negative 1 squared should be 1. 0 squared should be 0. 1 squared, 1. 8 squared, 64. What is step 4? Total. Total of what? All these. What's that add up to? 130. Step 5. Divide by n minus 1. What am I going to divide by here then? N is how many? How many are in the list? 5. So what's 5 minus 1? 4. So divide by 4. You get 32.5. What's this number called? That is the variance. How do we get from that to the standard deviation? Square root. Square root of 32.5 is 5.70. So you can see that is smaller compared to the 6.32 we had. So the standard deviation does distinguish between those sets. The one that's less spread out has a smaller standard deviation. We're about a minute and a half early here, but let's go ahead and take our break now anyway. Because the next thing is going to take a while to go through. So let's come back at about 4:29, and we'll start up on the second half of class.